right, so last class, I believe we had ended up with just the definitions of constructive interference and destructive interference. So you're going to need to add some diagrams. If you don't have room in here, make sure you just add on another page to your notes and then add those diagrams in there. Make sure they're labeled, all right? So for constructive interference, looking at the definitions that are here, all right, so constructive interference is interference in which displacements are on the same side of equilibrium position add together to form the resultant wave. And then the other definition that we had was for 11, destructive interference. I'm going to give you diagrams for these in a moment. Interference in which displacements are on the opposite sides of the equilibrium position cancel one another. Okay, so they're canceling each other out. Okay, does anyone need this information before I move to the images? Because I need to switch screens. Okay, so what we have here is constructive interference. So what this looks like, and yes, you have to draw all three of them. Okay, so I want you to listen carefully. So let's pretend this is a slinky, all right? Someone's holding this into the slinky. Someone is holding this into the slinky. And what happens is both of them are going to send a pulse out, okay? Real quick flick of the wrist. This person, they're both facing each other, so this one's going to send a pulse out on this side, and this person sends out a pulse on this side. So they are on the same side, okay? And they are approaching each other, all right, these waves. Emphasis, all right, here's the emphasis. Waves transfer energy only, okay? Not matter. So remember when we were looking at the transverse wave, we were looking at how the coils were moving. Coils would move up and down, but what would happen is your wave energy was traveling perpendicular to it. So if you're holding a slinky, that wave energy will go back and forth between those two people. But the waves in the coil, you don't have to let go of the slinky. They just vibrate up and down. So the matter does not actually move with the energy. Waves just transfer energy only. All right? So when you have persons holding this in, person is holding this into the slinky, they send the wave energy down, so waves are moving. What happens is, since that is energy only, that means that these waves will not bounce off of each other. If it was matter, so if I was like throwing two rocks at each other or two balls at each other and they hit each other, we know that matter cannot occupy the same space. All right, if there's matter there already, some other type of matter cannot come in and occupy the same space. Something's got to be moved out of place, all right? So if I threw two balls at each other, they are transferring energy and matter. And what happens is when those balls come together, they will bounce off each other, right, in a collision. Same thing with the car collisions that we're just talking about. Matter cannot occupy the same space as other matter, all right? So that's where things bounce off each other. But in the case of waves, since matter is not transferred, only the energy, that means that energy can pass through, all right? It can overlap. It doesn't bounce off. So this wave that was sent down will be moving to the right, and it will continue to the right. That's why down here, look, this was A, started over on this side, moving to the right. It's still moving to the right. It didn't bounce back. This energy, this wave, sent down, wave B, passes through, all right? So they pass through each other, all right? They can overlap, and then they pass through each other and continue on their journey. Now, when waves, that energy overlaps, what happens is that they sum together. Now, since these waves were on the same side, okay, then when they are summed together, in this case, they are adding because they are on the same side. So what we have is, let's say that this was an amplitude of 3 meters. If this has an amplitude of 3 meters and this has an amplitude of 3 meters, then what happens is when they come together, what would be the total amplitude here? What would be the total amplitude here? It's going to be 6, all right? But when they pass through, so when they overlap, they sum together, making a bigger wave, but then what happens is they are going to pass through each other. So again, as far as where this information goes in your notes, you have, this is constructive interference. So on your notes, number 10 for constructive interference, if you can, put it in this area. If you can't, then you need to add another page to your notes and put this down on the bottom. Make sure that you label these diagrams. This is for constructive interference. All right? So that's where that's going to go. Go ahead and take a minute, and then we will continue. All right, for destructive interference, which was number 11 on the notes, destructive interference. It's similar, all right? So again, looking at it as if it was a slinky with two people sitting on the ends. But what happens is when they send the waves down, they send them from opposite sides. So this person flicked their wrist in this direction, sends out a pulse on this side, and the other person on the other end sends out a pulse that's on the opposite side, okay? So constructive definition, think constructive is building. Destructive, you're tearing something down. And that's what's going to happen here. So same thing, matter is not being transferred, so these do not bounce off each other. It's only energy that's being transferred, all right? So again, what happens when they sum? In this case, you have them on opposite sides. So let's say that this is 3 meters amplitude, and this has 3 meters amplitude. What is going to be the amplitude when they overlap, when they meet and overlap? What will be the resulting amplitude? If this was 3 meters and this is 3 meters, what would be the resulting amplitude? It would be 0, because it's like 3 minus 3, right? 3 meters minus 3 meters. And that is why we see a flat line here, all right? But once they have passed that point, they're moving through each other, they will continue on with their same amplitude. So A will still have an amplitude of 3 meters, B will still have an amplitude of 3 meters. It's only for that time where they are overlapped do they sum together. All right, now, what would you expect to happen if, let's say this was 4 meters amplitude, so let's make it a little bit higher, and this was a little bit less. This is 2 meters. If this was 4 meters and this is 2 meters, what would you expect to happen? Okay, you're going to have 2 meters. And would that be on the top or on the bottom? Where would this amplitude, this wave appear? If this was 4 meters and this is 2 meters, it's going to be on top, because that's, so it's 4 minus 2, you're going to end up with 2, all right? So you only have complete destructive interference when your amplitudes are the same. Otherwise, it's destructive, but it will just be whatever's left over. So this, as far as this drawing, goes in number 11. Right here. Again, if you don't have room to add that, then put it at the bottom of your notes. So emphasizing again, and I'm doing this because this is a question that every year some of my physics students are missing, all right? When you are asked what does wave, or what is transferred by waves, it's energy only, okay? If you're asked what happens when you have 2 waves meet, make sure they are overlapping, the energy is overlapping, and they pass through each other, all right? They do not bounce off each other. So whatever path they are on, they will continue in that direction, all right? They don't bounce off each other because it's not matter, it's just energy. All right, next 2, number 12 and 13. Go ahead and write this down. This is where you would also need diagrams, but there isn't enough room here. Okay, so we're going to put those diagrams down at the bottom, right? It says, does fixed end termination represent waves moving from a less dense to more dense medium, or vice versa? Go ahead and write down that this is represents less dense, as far as your waves moving from a less dense to a more dense material. And then for number 13, where it asks, does free end termination represent waves moving from a less dense to more dense medium, or vice versa? Free end termination represents your waves moving from a more dense material to less dense material. Go ahead and write these down. Again, there is no room for the images I'm going to give you, so you're going to have to put those down at the bottom. Okay, but go ahead and write these down, and then I'll explain what that is. Fixed end termination and free end termination. All right, so going to the first diagram. Fixed in termination. Okay, so for fixed in termination, what this represents, it says a wave traveling from less dense material to a more dense material will be reflected off the boundary and transmitted across the boundary into the new medium, and the reflected pulse is inverted. So what you're looking at when we say your fixed in termination is where you have a wave moving from a less dense material to a more dense material. Think of a slinky. So think of it as we have just a slinky, okay, like this, slinky, less dense, right? Really loose, easy to move, yes? Okay, more dense material will be this coil, all right? So it does not, it's not as easy or as elastic as the other one, all right? This is denser material than what the slinky is composed of. Okay, now, let's say I was to connect this to this end, all right? So then we have your less dense medium connected to your more dense medium. And what I'm gonna do is I'm gonna have somebody hold the end of this coil and someone's holding the end of the slinky, all right? So think of this as all connected, one straight line, less dense, connected to a more dense material. Someone's holding the end of this and someone's holding the very end of this coil, all right? And what you're going to do is you're going to send, so this right here, this picture right here represents the slinky. This represents the coil, all right? They're connected in the center. Someone's holding the end of the thick coil. Someone's holding the end of the slinky, all right? Now, waves are not going to be sent down in both directions. What happens is this person that's holding the slinky is going to start a wave. It's going to start a pulse, send a pulse down, all right? So now you have your pulse that is moving through the slinky into the coil. It's moving from a less dense material into a more dense material, okay? So what's going to happen? I want you to think about this as an example. And actually, on your notes, right here, for this, let's say, for example, put down, since you don't have to, you're not going to put your picture here, write down for your example, put down sound. This is easier to see with transverse wave, which is what we're looking at in the diagram that I'm going to give you, but I just want to talk about it as far as moving from a less dense material into a more dense material. Sound going from air to a canyon wall. All right? So pretend you're out, okay? There's this vast space, a canyon, and far, far away from you, you can see a canyon wall. If I yell really, really loud, yell, okay? What is going to happen? What do you expect to hear? When I send out a sound, and then it hits a far canyon wall, what do I expect to hear? Do I expect anything to return? You expect to hear an echo, all right? So what that is basically you have sent out a wave. It encounters a more dense material, a more dense medium, and some of that is going to bounce back, all right? That echo is basically a reflection of that sound, all right? So when we're looking at this diagram, here, all right, you are sending out your wave in less dense material, which would be the air, all right, in a less dense material. And then what happens is that sound or that wave hits a barrier, something that is more dense, That would be your canyon wall, or in this case, a coil, that thick coil, all right? What will happen is you're going to have, so this is the initial and this is the after it hits this boundary. Some of that wave is going to be reflected, all right? Some of it actually goes through. Now you notice that as far as what goes through is still in the same direction. So this, as far as this wave was accreted up top, and then what goes through is still up top. But what will happen is the reflected, there is going to be reflection, so that's like your echo, but what happens is it's inverted. It's upside down, so it comes back on the opposite side, all right? So that's like a reverse where you had a compression. When it comes back, that's not going to be a compression, it's going to be a rarefaction. Where you had a rarefaction, it's going to be a compression, all right? On a transverse wave where it started up, it's going to come back upside down, all right? If you started upside down, it's going to come back right side up, all right? But as far as what goes through the transmitted wave, it's still going to be on the same side, all right? So it says a wave traveling from a less dense to a more dense medium will be reflected off the boundary and transmitted across the boundary into the new medium. So you're going to have part of it that's reflected and part of it that actually gets transmitted, okay? So like I'm talking in this room right now. Would somebody on the other side of the wall behind me in that room, would they hear some sound? Could they possibly hear me talking? Maybe not making out exactly what I'm saying, but could they hear what's going on in this classroom? Yes? Okay? Because what happens is that sound, that wave is still traveling. It's not like it gets to the wall and it bounces back into the room and nothing gets through. Some of it's getting through the wall, okay? So, but that wall is more dense than the air that's in this room. So most of the wave will be reflected back into this room, but some of it gets through. So what I want you to add to this, okay, you're writing this, you drew this. What I need you to do, star, highlight, in parentheses or something. Okay, write this down because this is going to be different for your free end termination. What's going to happen here is that we have some reflected, some transmitted. When you're moving from a less dense into a more dense material, more of the wave is reflected than is transmitted. More of the wave is reflected than is transmitted. There will be some of this that's transmitted that's going to go through, but most of it's going to be reflected. That's when you're moving from a less dense into a more dense material. More of the wave will be reflected than transmitted. So when you hear mumbling like on the other side of the wall, kind of muffled sound, so you hear talking but it's muffled, yes, that is the waves as far as the sound waves, it's getting through. It's just not all of it's coming through, all right? But yes, some of it is getting through. This is the less dense to more dense. This is fixed end termination, so number 12. Again, if you can't fit this in, which most likely you cannot fit this in number 12, put it on the bottom of your notes. All right, so for number 13, this is talking about the free end termination. Free end termination is just the opposite. So rather than going from a less dense to a more dense material, we're moving from a more dense to a less dense material. All right, so the diagram that you have for this looks like this. Blue represents the more dense material. So a wave traveling from a more dense to a less dense material will be reflected off the boundary and transmitted across the boundary into the new medium. So again, you're going to have partial reflection, partial transmission. But if you notice, look at the reflection. In a more dense material, what is reflected comes back on the same side. This started up top. It comes back up top. It comes back on the same side. All right? What is transmitted, what goes through to the less dense material, is also on the same side. But here's the thing. So when we went from a less dense to a more dense material, you think about it, I'm moving away from less dense to more dense material. That means you're going to have more resistance, right? If you hit something that's dense. If I'm trying to walk from the front of this room to the back of the room, but I've got like this room is packed with people, there's going to be more resistance. It's going to be harder for me to get through, right? So very little gets through. That's what we're talking about here when you're moving from a less dense to more dense material. On the other hand, if you're moving from a more dense to a less dense material, coil to the slinky, there's not as much resistance. It started from an area of high resistance and moved into an area with less resistance because it's less dense. In this case, what's going to happen is the majority of your energy, the majority of your wave is actually going to be transmitted. So you have in this, again, this is kind of opposite from what we said about number 12, all right? In number 12, with the fixed in termination, we said that more of the wave is reflected than is transmitted. In this case, and write it down, more of the energy is transmitted than is reflected. Okay, and that's what they're trying to show you by the wave. If you notice the wave here, the amplitude is a little bit bigger, which means more of the energy goes through. All right, and so this was the original. More of it goes through. Look at what's reflected. As far as what's reflected, there's less. All right, so when you're moving from a more dense material to a less dense material, more of the energy or more of the wave is transmitted than is reflected. That is for free end termination. So moving from, if you have fixed in termination, hold on a moment. All right, if you have fixed in termination, then what happens is, fixed in termination is up here. The reflected wave, it comes back on the opposite side, and more of the energy is reflected than is transmitted. If, on the other hand, it's free in termination, which means you're moving from a more dense to a less dense material, all right, the reflected wave will be on the same side, okay, still up here, and more of the energy is transmitted than is reflected, and that's because it's going into a less dense material. All right, this was number 13. So there's less resistance. It's easier for that energy to get through. All right, now that brings us down to number 14 and 15. You can go ahead and write that down because we already answered those. Which way does a wave reflect in a fixed in termination? So that's moving from a less dense to a more dense material. Your wave, whatever is reflected, will be reflected on the opposite side. Which way does a wave reflect in a free end termination? Free end termination, this is moving from a more dense to a less dense material. So as far as the reflected wave, it's going to be on the same side, same size as the original wave. All right, that brings us to the last part, standing wave. Define and diagram a standing wave, label all parts. I'm going to give you a minute to copy this down, and then we will talk about it. Standing wave, so go ahead and copy that down for standing wave. Make sure to get the diagram. All right, so standing wave, this is a wave pattern that results when two waves of the same frequency, same wavelength, same amplitude, travel in opposite directions and they interfere. So we are looking at, if you start a wave, and this is not going to be a pulse wave, so you don't just send down a single wave. This has to be something that is repetitive. So you need a periodic wave that's going to be, it's formed, all right, periodic wave where the source is continuous. The source of the frequency is continuous. So what you're producing is the same frequency, the same wavelength, and the same amplitude. Wave travels down, reflects back, all right? And that's what you have is these waves, the ones that are coming down, the ones that are reflecting, they are overlapping, all right? And what happens is you create what's called a standing wave. So frequency is high, and basically this thing is vibrating so fast as far as if you're looking at the waves on a string, so fast that it looks like it is doubled. But these are called antinodes right here. This section right here is an antinode. all right? This is an antinode. So an antinode is a point at which the largest amplitude occurs. You have constructive interference happening with the wave that's going down, wave that's coming back. You have constructive interference that is happening. They build on each other, and this is where you have the largest amplitude. But again, when you're looking at a standing wave, it is vibrating so fast that it looks like it's standing still. All right, and I'm going to show you that in a moment. So these are antinodes. So in this picture, this image that you have right here, how many antinodes do you see? How many antinodes are there in this image that's in the notes? Okay, top and bottom, just consider that whole loop as one. So you actually have, there's 1, 2, there's 2 antinodes. Your nodes are the points where you have destructive interference happening. So your amplitude, your frequency, your wavelengths are the same. But in these cases right here, this is where you have that destructive interference happening. So one of your waves was up, one of your waves was down, and what they do is they cancel each other out. So here is a node. And you actually count the nodes not only in the center, but the ones that are at the ends too. So there's 1, 2, 3 nodes here. Okay, 2 antinodes, areas of constructive interference where your amplitude is the highest, and then you have your 3 nodes, which is where you have that cancellation, that destructive interference. It's complete destructive interference because, again, the wavelength, the amplitude, frequency, all of it's the same. All right, amplitude's the same, it's going to completely cancel out. So node is point at which complete destructive interference occurs. So in this picture, we have 2 antinodes, 1, 2, 3 nodes. All right, so I'm going to draw a picture here. And I want you to tell me, first question is how many nodes or antinodes do you see? It's not perfect, but you can pretend for a moment that it is. All right, so for this picture, how many antinodes do you see? How many antinodes? Okay, areas of maximum amplitude, constructive interference, we have 1, 2, 3, 4, 5, 6. So 6 antinodes. What about nodes? How many nodes do you see? Good. Nodes is 7. Remember, you count your ends. So 1, 2, 3, 4, 5, 6, 7. And just a note, your nodes, you always have one more node than you have antinodes. So if I have 6 antinodes, then I'm going to have 7 nodes. If I have 4 antinodes, then I'm going to have 5 nodes. All right, it's always going to be 1. Make sure your nodes, you're counting the ones that are on the ends also. Okay, so from beginning to end. All right, I'm going to switch to a video of standing waves. I'm not going to turn the sound up, but I'll just play it and tell you what's going on, or the part that you need to know.
So what we have here is a frequency.
So as I was saying, what happens is you have, when you're creating standing waves, you need your source, whatever is producing the frequency, has to be something that is going to be consistent. So you need that repetitive motion, periodic motion. So what he has here is a frequency generator, and basically what it's doing is it's causing this, you have a string that is attached to this, and it's causing that to go up and down, all right, at a certain rate, a certain frequency, and that's going to produce the wave. Now, just turning this on and making the string vibrate up and down does not necessarily mean that you're going to produce a standing wave. Okay, so in this case, you don't really see a standing wave being created. All right, we see the rope vibrating, but you don't see the clear areas of antinodes and nodes. All right, so what happens is, and that means what happens is even though you have waves going down, you have waves coming back, that reflected wave, they are not properly overlapping, all right, in order to form that standing wave. So you have to find the right frequency in order to get your standing waves formed. And one of the things that it's going to, your frequency is going to vary depending on the length of, in this case, the string, all right? So you change the length of the string, you're going to have the frequency that is necessary to produce the standing waves is also going to change. All right, so here, he's going to change the frequency, and there you have your standing wave. Does everyone see? Okay, so how many antinodes do you see? How many antinodes? 2 antinodes? Good. And how many nodes are there? 3. All right. So what you can do is you can, so that's this is your standing wave. What you can do is continue to increase the frequency until you can produce more. The greater the frequency, the more nodes and antinodes you can get. So let's see. Okay, so this one is 3 antinodes. And how many nodes? How many nodes? 4. Okay, he's going to increase the frequency, I think, one more time. All right, take a look at that one. Small amplitude, but it's still standing wave. So what do you see? How many antinodes do you see here? Good, 6 antinodes. And then how many nodes? 7. Good, 7 nodes. That includes, again, the end. All right, so that actually completes your notes for this section. You are, as far as your homework, you're going to listen to the video that was pre-recorded to complete the notes on the types. It's going to go over the types of waves and different properties of waves that we'll talk about a little bit next time. Does anyone have any questions on this part?